Okay, so we're gonna work on some harder examples of these optimization problems. So last night's were the easy ones. So we're just some harder ones. So let's look at this one. It says that square-based, box-shaped shipping crates designed to have a volume of 16 feet cubed. The material used to make the base is twice as much as the sides, and the top is half as much as the sides. What are the dimensions of the crate that minimize the cost of the materials? So, if you were following my lead and approaching these with the right frame of mind that I was trying to encourage you to, what's the first thing we think about as we get started on this problem? What's that? Well, that's pretty obvious, right? A minimum. Yeah. Dimensions of a crate, X, Y, and Z. What is going to be our way of thinking about this? What's that? Find our optimization rate. Yeah. So an equation? One more try. Function. Okay? A function whose dependent variable is the thing we're trying to maximize or minimize. A function whose dependent variable is the thing we're trying to maximize or minimize. The first half of the problem, we'll be writing that function. The second half of the problem, we'll be using that function to answer the question. Yeah? Yes, I am. So if we want an anchor, something to hold on to, we're going to be creating a function whose dependent variable is what? Whose dependent variable is what? Or whose output is what? Yeah, what in this case? What will our dependent variable for our function be? That's not a quantity. What quantity? What kind of thing? Volume, temperature, distance, velocity. Surface area. We're trying to minimize surface area. So we want a function of surface area. Okay, therefore I want a cost function. A cost function. A function that gives us costs. We're trying to minimize costs, so the whole problem is going to revolve around a function that gives us the cost of the box. Okay? So we got to keep practicing that. Okay? So we want to get a cost function. So can we get something going here? Something going, some kind of just maybe a cost equation, even if it has lots of variables and it's just rough. How are we going to calculate the cost of this box? Maybe we need a picture. So what do we know about this box? Square base. What do you want to call the side like the square base? X, I agree. And then what about the height of it? Sure. Y, H, whatever. Okay, cool. So this is good stuff. So now we want to come up with this something, just get going here. We know it's going to center all in a cost function, so let's just get something down that calculates the cost of this thing. Yeah? Okay. Okay. So you're saying that the base has an area of x squared, but is that the cost? Okay, so we need to, so it doesn't, all it tells us is the cost relative to the sides. So maybe do we want to pick, what is the cost of the sides, say, per square foot? One? So we could use 1. We're not really even sure that it's 1. So maybe can we just use like A? Let's say that the cost of the sides is $8 per square foot. And if you used 1, we're going to see what happens to this A. So 1 would be okay, but we use general as we can. We don't know, so we'll call it A, $8 per square foot. So what is the cost of the base? 2A? So just 2A? That's per square foot. So how much is the total cost of the base? Then 2A times the area, right? So you take the cost per square foot times the area, you're going to get the total cost. So this is how much the base costs. Does this make sense? All right, so why don't you finish this? See if you can finish this cost. This is just an equation, right? So we're just getting something down. We're just getting something down to start. Okay, right here, with the cap on. Yeah, yes, you with the cap. Can you add to this cost? Can you give me some more of this? Okay, well, what was this? This was the sides? Was that? The sides and the base. Is it the sides and the base? And what about the base is this? Okay, what about next to him? Can you give me some more of this? 4a y squared. What do we think? So what are you intending to do there with that term? And what about the side panels of the box are you adding on? Square footage. Adding the area of the side panels. Agree with that? No, what do you think? 4a? 4axy. And what is that calculating for axy? The cost for the total of the 4 sides. Okay, because the cost per one square foot is A, and then each side is xy, and then there's 4 sides. So this was the fact that the base had double the cost of the rest. This is the fact that we have 4 sides. You see that? Okay, what's left? Plus half A x squared. Agree with that? Okay, so we've got a cost kind of equation. We need a cost function. So what's wrong with this? Why do we need to keep refining it? We have 2 variables. We have x and y. So we want to get it just in terms of x. And so in order to get it just in terms of x, we need y in terms of x. And what is going to help us do that? What's going to help us? We need to get y in terms of x. Okay, so that's some other information that we haven't used yet, which is the volume is 16 feet cubed. So if the volume is 16 feet cubed, so this is like side work here. So the volume is 16 feet cubed. How can we get y in terms of x? What is the volume of our box? X squared y equals, so y is 16 over x squared, okay? So we can put that here. So then we'll have it. We'll have our cost function, 2a. And can we combine these 2 terms? what is this? 2.5a, is that 5 halves a? So 5 halves a, x squared, that's adding together these two. Let's not do that. Let's write it so we can see what's going on. 2a x squared, cost of the base, plus 4a x times 16 over x squared, plus 1/2 ax squared, cost of the top. Anything else we need for our cost function for it to be complete? Yes, there is. What do we need? Nope, I'm just talking about having the full cost function. What other important thing do we need to have for this? Applicable domain. Applicable domain. We need the domain, right? So we need what are all possible x values. So what's the smallest x can be? It's not really realistic, but 0. And how large could x be? Well, this is a little strange because the constraint is on volume, right? So we think about y getting smaller and smaller and smaller, and our total volume being 16. So how big could that square base be with a volume of 16 as y gets smaller and smaller and smaller?
Take y to be equal to 0 and just x squared equals 16.
No, but it's volume, not area. So if you think about a really, really small y, what's that going to mean for x? If you have a fixed volume of 16. It's going to get really big, right? And then we can make y half as small as that, and x will be even bigger. So really, there's no kind of largest value of x. It doesn't make sense to have a really small y. I mean, it's going to be a totally unpractical box. But in terms of how mathematically how big x could be, really it can be any value as long as you make y small enough. Does that make sense? So for any large x you could pick, there's a small enough y so that this volume is 16. So it's kind of like infinite. And so what does this tell us about this particular problem? So in problems like this, you have this domain where that's really your x domain. Both of these n values are not practical, right? Not practical. X being 0, meaning you just have like a tall stick that can't hold anything. Or x being infinity, it's just this, huge flat piece of paper with hardly any height. Okay? So we're really looking for when we solve this, we're really going to be focusing on critical values, not the n values, right? N values don't make practical sense for this box. Okay? So we're really going to be looking for critical values. How do we get critical values? So we know we're going to do critical values and n values of the applicable domain, but we said those don't really make sense, okay? They give volume of 0 in both cases. So critical values. Derivative is 0, okay? So here we go. 4ax plus, what do we have? 64a over x. This would be minus 64a over x squared. Check my math. Plus ax. So I had x to the minus 1, 64a Yeah, negative x to the minus 2. That's right. And critical values we want are where the derivative is. We're looking for a place where the cost does what? We're looking for a place where the cost does what in terms of thinking about changing cost? Pause, right? We want a pause in the cost. A pause in the cost is going to be like a minimum or a maximum. And to get a pause, we know we want the first derivative to be 0. Okay, so now look what happens to a. If we're solving this for equals to 0, then a, we can just divide and it goes away. It's not dependent. So this critical value is not dependent on whatever cost per square foot we have for the side. Okay, so what do we have? We have 5x equals 64 over x squared. And then x cubed equals 64 fifths. And x equals the cube root of 64 over 5. Okay, but that's not how we, that's not how we talk and measure things. So let's get a value for that. What is the cube root of 64 over 5? Did I do all the math right? Yeah. No, I just x to the minus 1. It's just x, it's just 64a over x. Right? So I simplified that before I did the derivative. So it's negative x to the negative 2. Other questions? Did I do the math right? Yeah. 4 plus 1. 4 plus 1. Okay, so what is the cube root of 64 over 5? Yeah, I don't mean for you to figure out in your head. I'm looking for a decimal approximation. 2.34? 2.34. 2.34 what? What is x a measure of? Volume? Cost? No, that was our dimension of our base, right? That was our square dimension of our base. So 2.34 feet. Okay? Okay, so because we don't have anything else here to verify, we don't have any n values that make sense for this cost function. We get this 2.34, it's the only critical value we get. Let's go ahead and verify what kind of critical value we have. And so we can do that with a second derivative. So second derivative is 4a b plus x to the minus 2, 128 over x cubed. Plus a. And that's a also. Equals 0. No, not equals 0. We're just seeing what its sign is, right? So 2.34, when we put that into the second derivative, is that going to make it negative or positive? So if we plug 2.34 into the second derivative, so the second derivative at 2.34, all we need to know is if it makes it negative or positive. What do you think? Positive, right? Everything's positive here. Everything's positive. Conclusion? So we got the second derivative at 2.34 is greater than 0. What does that mean about the first derivative? The first derivative is increasing, right? If the second derivative is 0, the first derivative is increasing. And that means what? Minimum, right? Turning counterclockwise. Turning counterclockwise. Concave up. All right? So this verifies that this gives us a minimum cost. And so how do we get the other dimension then? Piece of cake. We got this expression y equals 16 over x squared. So we can come up here then and get corresponding y. What is that? Nice and loud. 2.92? Someone else get that? Okay, and if we wanted to know what that minimum cost was, what would we do? Yeah, the cost function does exactly that. And all we'd have to do is take our 2.34 feet for the length of the base, put it into the cost function, and then it would be an expression with a in it, right? So it would be in terms of whatever the cost per square foot of the sides is. Okay, but so our dimensions of the base would be 2.34 on a side and 2.92. We confirmed that it was minimum cost. It's concave up. Anybody have a question on this example? Okay, let's try another one. Okay, so here's one. An A-frame barn is to be built so that it's 30 feet high, 40 feet wide, and 60 feet long. Okay? A rectangular room is to be built inside the barn so that its ceiling abuts the roof. What dimensions should the room have so that its volume is as large as possible? So here is a picture so you understand. So A-frame means that it's basically just looks like an A, right? So it's all roof, right? It's got a pitched roof on one side, pitched roof on the other. Okay? And that's 30 feet high is going to be this to the kind of the apex. And then 40 feet wide is going to be our from A to B here. So our 40 feet. 60 feet long is going like back into the screen, right? Going back that way, behind the screen. What dimensions should the room have so that its volume is as large as possible? Okay, so what are we thinking about when we start this problem? What are we thinking about when we start this problem? Somebody do. What's that? What we're optimizing, okay, which is what? Volume. Okay, so therefore, what is our goal, our centerpiece of this solution? Someone started saying it. A function that has what? The dependent variable of our function will be volume. Okay, a function whose dependent variable is volume. A function whose dependent variable is volume. We're going to spend the first part of the problem creating that function, and then the second part of the problem using that function. That's the centerpiece. Centerpiece is a function whose dependent variable will be the volume of this thing. Train yourself to do that, because it gives you an anchor with all this information flying around. It gives you an anchor to work on these problems by. Okay? All right, so volume. Let's just start with some kind of equation. So anyway, so let's see what happens here. So what is it that can change here? So what is it? Why is it that we have different possibilities? Do you see why we have different possibilities here that we're trying to find the maximum volume? So it's like we can have like a real short squatty room like this, or a real tall narrow room. So here's why there's actually a question here. It's like, how do we build this rectangular room? Okay, so that we get the biggest volume possible. All right, volume equals. Rectangular, solid, right? Length times width times height. Okay, good start, good start. Do we know any of those? What do we know? We know the length. What is the length? The length, that's that dimension in and out of the screen, like behind the screen, how long that room is this way. That stays constant at 60. But what about the width and the height? Those are changing, right? You're watching it, right? You're watching those change before your eyes. So we're asking. So what do we want to? So we want to get this volume in one variable. Volume in one variable. So if you notice here in my animation here, this little illustration, that I have this x here, and it's actually easiest to do this as a function of that x, even though that's neither the width nor the height. And if we're going to do that, then what do we need to get? So I'm going to do volume in terms of that x, because I've done this problem before, and I know that's convenient. I know that's really helpful to use that as my changing input quantity, or independent variable. So then what is it going to mean for what I've got here, 60 WH? I have to find width and height in terms of x, right? So I'm going to have to figure out what the width is in terms of x, and the height is in terms of x, and then I'll have it. Okay, see if you can do it. So we want to get width in terms of x, and the height. Work together. We got to do some math here, right? Do some geometry. Some math. How are we going to get the width in terms of x and the height in terms of x? Then we can write our volume as a function of x. Go. Work together. Sitting and staring is not an option. You're making progress or you're working with somebody else and getting help. Sitting and staring at the screen is not an option. It's just derivative 64a x to the minus 1. So I'm just doing the derivative of x to the minus 1. That's all I'm doing. Just negative x to the minus 1. But it's times x, so it's 1 over x. Simplify first. X over x squared is just 1 over x. Right? Yeah, but that's something we should look at later. So stay focused on like the setup here. You can figure that out later. Did it? Either one of them? But, okay.
She's talking about your x squared is a squared.
There's your key. Okay, the width should have been no problem. What did you get for the width in terms of x? 40 minus x? 2x. You see this minus 2x? One on each side, right? You see that? Do you see that? That's minus 2x? One on each side. 40 minus 2x. What about the height in terms of x? What's the key here? So you got to recognize the relationship that you have going on here that's going to make it really easy. Height and x, right? 30 and 20. What's going on here? Height and x, 30 and 20. Isn't the height relative to x the same as 30 relative to 20? Yeah, so you have proportionality. You have similar triangles. Do you see that in geometry? Similar triangles. So what could we do? We could say that the height over x is what? Yeah, it's basically a 3-to-2 ratio, right? 3-to-2 ratio. So the height in terms of x is 1.5 times x, right? Oh, wait, height, yeah, height. So the width equals, and the height equals basically 3/2 x, right? Because that no matter where that is in the room, you're going to maintain that 3-to-2 ratio of the height to x, which is similar triangles here, right? Similar triangles. The whole half triangle is 3-to-2. This will always be 3. This will be 3-to-2 as well. Okay, so what's our volume function? 60 times 40 minus 2x times. Okay, are we done with the volume function? Some are saying no. Why not? The domain, right? Applicable domain for this. X goes from lowest possible x, greatest possible x. 0 to, okay, and then we look at those n values and we think, okay, x is 0. Is that going to be the biggest room? No. X equals 20. Going to be the biggest room? No. Those are non-rooms, right? Mathematically, perfectly fine. X equals 0 is mathematically works fine. X equals 20. Mathematically, it works fine. But they're both non-rooms. There's no room there. There's nothing. So again, we'll be looking for critical values. Looking for a critical value that will give maximum volume. We won't do that. So the rest, I think you can do. But here, again, centerpiece of the problem is our function that gives us volume. We're looking for a critical value that will give the maximum volume. Questions on this one? Domain, all possible values of x. What's the smallest x could be? What's the biggest x could be? Right there. Can't be any bigger than 20. Okay, questions on this one? All right, let's try the pond. Okay, so we're going to do the pond. We're going to review trig on the fly here, okay? So we're going to work on this one. It's all about trig. So as we're doing this problem, we'll be reviewing trig kind of on the fly simultaneously. Okay, so in one part of an outdoor race, competitors come to a circular pond with a radius of 1.8 kilometers. They must make it to the point directly across the pond. That's bigger. There we go. Okay, they must make it to a point directly across the pond at the other end of the diameter by swimming and or running around the pond's edge, which is rocky and uneven. One racer, Josie, can run 4 kilometers per hour around the rocky edge and swim 3 kilometers per hour. How should she choose point P, as shown in the diagram, to complete this part of the race as quickly as possible? Okay, so tell the person next to you, what is going to be the central feature of the solution to your problem? Talk. What's going to be the central feature of, or the central thing of focal point in your solution to this problem? Go. Tell the person next to you. Okay. How about back here in the blue jeans jacket? Yeah. What do you think? What will be the central feature of the solution to this problem? What's that? No. How about right next to her? Right next to her. In the brown slip-up jacket. Black. What do you think? What's going to be the central feature of the solution to this problem? I still haven't gotten through to him. Chance, you try. I'm talking about in the solution. What's going to be our focal point, our centerpiece, our most important thing?
Like how we're gonna weight it?
No. No. Anyone else want to try? What's that? Okay. So a function whose dependent variable is her time to get across. A function whose dependent variable is her time to get across. It's not trivial, folks. It's not trivial, because if you're focusing on something other than that, then there's gonna be so many distractions. Okay? We need a function whose dependent variable is the time for her to get across. All right? What's going to be the overall structure of that? So we need a function with dependent variable, what? Time. Total time. Okay? A function with dependent variable, total time. That's what we want. Okay, so what's the structure of that function going to be like? Time equals what? Let's just get something down. Let's just get started. Time equals what? Time it takes for her to run plus the time it takes for her to swim. I love it. Time to run, one thing at a time, plus time to swim. Okay, so it says that she can run on the edge of this pond 4 kilometers per hour. So how much time is it going to take her to run at 4 kilometers per hour? Okay, so she's going to have, no. We're making a function, right? A function of, we haven't decided of what yet, but a function means there's all these different possibilities, right? And we want the best possibility, in this case, the minimum time. Okay, so how do we calculate the time for her running part? The time for the part of this where she's running. Yeah. How far is she running? No. Do you see the red? The red is where she's running and swimming. Do you see? She's gonna run part of it and swim the other part. So she's gonna stay on this red path. So she's not running halfway around the circle. How long will it take her to do her running part? Yeah.
The time it takes her to run multiplied by the change in her run.
But we're asking how long the time is. And so you said the time times something. But we're trying to calculate what the time of her run is. Yeah. Distance divided by her speed. Yeah, because distance is what? At a constant rate, distance is constant rate, speed times time, right? Or v times time. So time is distance. So distance for the run divided by her rate for the run, which is what? 4? 4. Okay, what about the time for her swim? There we go. Okay, so the distance for the swim divided by 3. Notice how we're coming at this one baby step at a time. For your function that you're after, just write the most generic structure of it that you can. Start easy, make it easy on yourself, and then make little bites at it, right? So make like little changes at it to until it's refined. Okay, so now the question is, what variable do we want for this? What variable do we want to decide where she's going to stop running and start swimming? So really, what variable is going to determine point P? And I told you this was about trig, right? So do you see a convenient quantity that determines point P? Okay, so because of time's sake, so theta. The angle theta from here, the right side of the circle, swept up counterclockwise, is a nice choice for which determines a particular point P where she would stop running and start swimming. Okay, so what is her distance run if for an angle theta? Well, it's this arc length, right? And do you remember what we talked about with trig? That arc length, where does theta come from? Theta comes from arc length measured how? Radius lengths, right? Radius lengths. Okay? So what is the distance? But we want her distance what? In meters or kilometers. Okay? We want her distance in kilometers. So theta is her distance in radius lengths, and each radius is 1.8 kilometers, then what's her distance run in kilometers? Right, so theta is telling you how many radius lengths she runs. And how long is each radius length? 1.8 kilometers. So how many kilometers does she run? 1.8 times theta. Right, theta is a measure of how many radius lengths of arc length. If each radius length is 1.8 kilometers, then the total kilometers she runs is 1.8 theta. Should make sense. Okay, what about the distance of the swim? So this distance of the swim, I'm going to call this C. This is going to be Pythagorean theorem. Okay, do you see this right triangle right here? So what is this base of this triangle right here? Well, it's the radius plus 1.8 over here, always 1.8, plus what is that right there? Okay, in radius lengths, it's cosine, but how about in kilometers? From here to here. 1.8 cosine. That distance from there to there is cosine theta measured in radius lengths, and if each radius is 1.8 kilometers, then to get kilometers, it'll be 1.8 cosine theta. And then what's this in kilometers right here? 1.8 sine theta. So this is going to be a really ugly expression. It's going to be this thing squared plus this thing squared, square root. And we're going to call that C. And then we have it. That is T, the time, as a function of theta. Total time for her to get across is a function of theta. All we need is the applicable domain. Theta from what to what? Least theta. 0 means what for her race? Swims the whole way. 2 pi, meaning she runs the whole way. See that? So these n values are definitely important because they're both legitimate things that she could do. She could swim the whole way, that's theta equals 0. She could run the whole way, that's theta equals pi. Gobble, gobble. Have a great break. I'll see you on Monday.